Hello GATE aspirants, welcome to part 4 of GATE Nuclear and Particle Physics series. Question number 9. The decay process, this process is given and it violates. So N, proton, electron and neutron. So this is given. Now first of all let us calculate all this for these options. So baryon number, this is baryon 0, 0. So baryon number B is conserved. So delta B is equal to 0. So it is conserved. Next we have lepton number. So 0, 0. These are not leptons. This is lepton and minus 1. That means lepton number is also conserved. And both are electrons. So they are conserved here. Next we have isospin. So for isospin we have for neutron it is minus half. For proton it is plus half. Electron 0 and 0. So this will be delta I3 will be, this will be plus half minus minus half. So this will be minus 1. So isospin it's not conserved. Next strangeness 0, 0. All these particles are not strange particles. So this is conserved. So option C only, it is not conserved. So it violates isospin. Next question. The isospin I and baryon number B of up quark is. So for up quark I is equal to half and baryon number is 1 by 3. So option D is correct. Next question. Consider the scattering of neutrons by protons at very low energy due to nuclear potential of range R0, given that cot of k R0 plus delta is nearly equal to minus gamma by k, where delta is the phase shift and k is wave number and minus gamma is the logarithmic derivative of the deuteron ground state wave function. The phase shift is. This function is given, so I can take reciprocal on both sides. So tan of k R0 plus delta, it will be nearly equal to minus of k by gamma. And at very low energy, if we are considering very low energy, then at that point tan theta I can write it is nearly equal to theta. So that means k R0 plus delta, it will be nearly equal to minus k by gamma. So that means delta is equal to, delta will be nearly equal to minus k upon gamma minus k R0. So here option A is correct. Next question. 12. In the beta decay process, the transition 2 plus to 3 plus is allowed by Fermi and Gamow-Taylor. So here we have to consider these two selection rules. For this particular transition, this delta Z is equal to plus minus 1 and parity is not changing. So for parity, there is no change. So this is for the given transition. Now we have Fermi selection rules. So according to Fermi selection rule, delta Z is equal to 0 and for parity there is no change. And we have Gamow-Taylor selection rules. These are delta Z can be 0 or plus minus 1 and for parity there will be no change. So here there is no change in parity and delta Z is plus 1. So these are not allowed by Fermi but allowed by Gamow-Taylor selection rules. So option C is correct. Next question. The electromagnetic form factor F of Q square of a nucleus is given by this expression where Q is a constant. These functions are given where rho r is the charge density. The root mean square radius of the nucleus is given by. So this expression is given to us and F of Q square is also given. So let us take first derivative of this. So for this expression, if I am considering derivative of it, so d of fq square upon dq square. and we will consider it at q square is equal to 0. So let us first calculate derivative only. So this will be exponential of minus of q square upon 2q square into minus of 2q square. And if we are calculating at q square is equal to 0, so at q square is equal to 0, the same thing df q square by dq square, it will be exponential raised to 0 is 1, so this will be minus of 1 upon 2q square, 2 capital Q square. Now f of 0 is equal to, if we put q is equal to 0, then this integration over rho of r d cube r, this comes out to be 1. Now this theory of this I found in a research paper, so it was not from a book specified for the syllabus of GATE. It was taken from that research paper that I found. So I will put link for it in the description box. Now the average value of r square is equal to minus of 6 f of 0. Then we have df q square by dq square when q square is equal to 0. So this will be minus of 6 upon 1 into we have 1 by 2q square, and this comes out to be 3 by q square. And for RMS value, this will be square root of this, so that will be RMS value, and this will be root 3 by q. So option C is correct. Next question, 43. Consider the decay of pion into a muon and an antineutrino. So in the pion rest frame, so this pion is at rest, and it is then emitting two particles, muon and muon neutrino, and masses are given. The energy of the emitted neutrino to the nearest integer is. Now if initially it is at rest, that means its initial momentum is 0. That means final momentum of this muon and neutrino, it will also be 0. So that means addition of these two, it will be 0. So in magnitude they will be same. So magnitude of muon, momentum of muon, and that of neutrino, it will be same. Now let us apply, so this here we have applied conservation of linear momentum. Now let us apply conservation of energy as well. So energy, initial energy, it will be mass energy, because it is not moving, it won't have any kinetic energy. So mass energy is m pi c square, and final energy will be energy of muon plus energy of neutrino. Now these energies will contain both kinetic and mass energies. So from here I can write m pi c square minus energy of this neutrino, it will be equal to E into E of mu. Now we have energy of neutrino, since it is not having any mass, so that means mass energy will be 0. So this I can write as C into its momentum. So C into momentum, that will give us total energy. But here we have momentum of neutrino and muon, they are same, so this can be written as p mu as well. So we will substitute this in this equation. So that means m pi c square minus of c p mu, that will be equal to E mu. Now we can take square on both sides, and let us expand this. So this first term will be m pi square c raised to 4 minus 2 m pi c square into c into p mu plus c square p mu square is equal to, on the right hand side we have energy of muon. Now energy of muon will have two terms, kinetic energy plus mass energy. So kinetic energy is p mu square c square, and mass energy will be m mu square c raised to 4. So these two terms will cancel out. Throughout we can cancel c square here. So finally we will get m pi square minus this term m mu square whole thing into c square, and that will be equal to 2 into this term c into p mu into m pi. So that means c into p mu is equal to m pi square minus m mu square upon 2 m pi. This whole thing into c square. So this is the direct formula that you can use. If it is given that initially the particle is at rest and then it is dividing into two particles, then this formula can be directly used. Now, energy of muon is asked. So that will be, now see, energy of neutrino is asked, and this is c into p mu, but c into p mu is equal to c into p neutrino as well, right? So this will be E nu only. So it will be P nu. So you can use this equation directly. Now m pi is equal to 139.6 square minus 105.7 square upon 2 into 139.6 whole thing into c square. So E nu is equal to, after solving this, you will get 29.78 mega electron volt, which is nearly equal to 30 mega electron volt. So rounding off to nearest integer, this will be 30, and 30 is the answer for this question. So these were all the questions from GATE 2013 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.